given by Maarten De Boeck, and this talk will be about Neumaier graphs. So the floor is yours.
Okay, thank you very much, and thank you for giving me the opportunity to present my research here. So I will indeed be talking about the Neumaier graphs, and this is joint work in two various subsets with Aida Abiad, Walter Kastrijk, Bart de Bruyn, Jack Cole, and Sanne Zijlemaker. So I will, let's say, first introduce you Neumaier graphs and then talk a bit about existence and non-existence conditions. And maybe the first two slides will be an insult to the audience, then just ignore me. But just to be sure we're all on the same page. I start with regularity in graphs. We have k-regular graphs when each vertex is connected to k other vertices. Graph is edge-regular if every two adjacent vertices have lambda common neighbors, and if the same holds for two non-adjacent vertices, they are co-edge regular. We think this is very important because so we can define strongly regular graphs, which are regular, edge-regular, and co-edge regular. And I see for the third consecutive talk we have the Petersen graph. I'm sorry for that, but it's too nice example to not show. So this is a strongly regular graph on 10 vertices. Next to it, I have the 3x3 Rooks graph, which is a strongly regular graph on 9 vertices. But I'm sure that most of you know about strongly regular graphs. So what's important here is that I will be talking about also regularity of subsets. Now, a vertex subset of a graph is irregular if every vertex outside of this subset has precisely e neighbors inside the subset. So, for instance, this outer cycle of the Petersen graph is a one regular subset because every black vertex has precisely one yellow neighbor. Right in the Rooks graph, we see that the yellow subset is a one regular clique, again because every black vertex has one yellow neighbor. Now the difference between these two examples is that on the right, the yellow subset forms a clique, and on the left it does not. And in the Petersen graph, we can see there are no regular cliques because the largest cliques are edges and they are not regular. Okay, so why do I introduce this? Because Neumaier in 1981 proved the following very nice theorem. He showed that if you have a graph which is both vertex transitive and edge transitive, and it has a regular clique, then it must be strongly regular. Now, it is quite clear that the vertex transitivity implies the regularity and the edge transitivity implies the edge regularity. So in a sense, these two combined with the regular clique give you the co-edge regularity. And the question that Neumaier asked, very natural in this sense, is whether he could weaken the conditions from this theorem a little bit and still have the same result. And he asked whether instead of vertex transitivity, it would be possible to ask just regularity, and instead of edge transitivity, just edge regularity, still together with this regular clique, whether you would still have a strongly regular graph. So are regular edge regular graphs with regular clique necessarily strongly regular? So in his honor, both the theorem and the question, we ask such a graph a Neumaier graph. And if it is indeed not strongly regular, we would call it a strictly Neumaier graph. Now, such a Neumaier graph has a bunch of parameters. Vk lambda, or well, the classic parameters of an edge regular graph. V vertices, k regular, lambda edge regular. And now we also have the E and the S pointing to a irregular clique of size S. And well, if you want to search for such graphs, the first thing you're going to do is ask yourself, are there indeed strictly Neumaier graphs? That's the question that Neumaier asked. But you're going to restrict your search, and you're going to ask yourselves, for which parameter sets could I find such strictly Neumaier graphs? And well, as people in combinatorics and graph theory, what we like, what we're good at is counting. And the first results are feasibility conditions. Conditions on for which parameters you can indeed have such graphs. And now Neumaier graphs are for sure edge regular graphs. So these first two conditions are just about edge regular graphs and are what I call folklore. I mean, they're known for ages. That, for instance, v minus 2k plus lambda must be positive. That the parameter of regularity times the parameter of the edge regularity must be even. We know this. So it restricts your search. Then the following three conditions are already due to Neumaier. And these first two conditions, the conditions 3 and 4, essentially tell you that v and lambda, or two others if you want to, but you can write two parameters in function of the three others. So you don't have 5 free variables, but you can express 2 in parameters as a function of the three others. It's natural to take v and lambda for this, but you could pick others. Also, you have this condition, this expression must be positive. Now, Evans, Gordionov, and Panasenko also found some conditions, and what we know that for strictly Neumaier graphs, we can improve on conditions 1 and 5. But moreover, we also have conditions 6 and 7, stating that the clique cannot be very small and the parameter E cannot be too close to the size of the clique if you want to have a strictly Neumaier graph. So with this in mind, with these 7 conditions, what you're going to do, you make a table. So if you restrict the number of vertices to at most 39, these are all possible parameter sets, admitting the 7 conditions for strictly Neumaier graphs from the previous slides. So that's already an improvement for your search space if you want to look for Neumaier graphs or strictly Neumaier graphs. So that's good. But the first thing that we could do was, in fact, find some more counting results, so some more feasibility conditions on the parameters. So in case you have a Neumaier graph, then this quadratic expression must be at least 0. In particular, for a strictly Neumaier graph, it must be larger than 0. So remember the previous condition, the previous inequality was a linear inequality. Now we have a quadratic inequality on the parameters. Now, as an immediate follow-up to this, we could also prove a second condition on the parameters. So if you have this parameter set for some odd s, you could check whether it fulfills this condition from the theorem above, and you will see that this is indeed positive, but you will find precisely 2. Now, in case you find precisely 2, this theorem doesn't tell you anything, it doesn't exclude the parameter set, but from the proof, you still know a few things, and in fact, this allows you to disprove the existence of Neumaier graphs with this parameter set. So good, we have these 2 results about non-existence. And especially for the first one, you could ask yourself, is this any good? I mean, do we have parameter sets that were previously admissible, but no longer anymore now. And yes, indeed, for instance, this parameter set, depending on an integer a, at least 3, and another integer n, at least 2, fulfills all 7 conditions from before, but doesn't fulfill the condition that we just imposed. So indeed, it kills, if I can use this word, several of the parameter sets. Same thing here for this infinite family of admissible parameter sets. And for strictly Neumaier graphs, I can also give you 2 infinite families of parameter sets which admit the 7 conditions we knew before, but do not admit the parameter, the condition that we just proved. You could ask yourself, is this a lot? Well, if I look at the table from before, you see 5 of these cases we don't have to look at anymore. They're now disproven to exist. And in general, for the 99 smallest cases, well, with the number of vertices at most 64, 13 are now no longer admissible. So that's good. We have some results about non-existence. But then, of course, it's time to talk about existence of Neumaier graphs. Because, and this is maybe the surprise, they do indeed exist, these strictly Neumaier graphs. So remembering, this is a strictly Neumaier graph because it is regular. You see it is 9 regular. It is edge regular. In particular, it's 4 edge regular. There is a regular clique. You see here the clique in the middle, it has 4 vertices, and each vertex not in this clique has precisely 2 neighbors in the clique. But it is a strictly Neumaier graph because it is not co-edge regular. Indeed, if you check, these 2 orange vertices are not adjacent, but they have 8 common neighbors, while on the other hand, the 2 green vertices are non-adjacent, but they have only 6 common neighbors. So indeed, this strictly Neumaier graph exists. Now it were Greaves and Cole who in 2018, and that's 37 years after Neumaier's question, who showed that there are indeed strictly Neumaier graphs, and they proved that there are infinitely many. The example I showed you is from a result from Akademgorodok and Panasenko, who showed that there is an infinite class of strictly Neumaier graphs with these parameters. And notoriously, they have the E different from 1, and this is so far the only family known with E different from 1. Now, as I said, the graph on 16 vertices that I showed you in the previous slide is the smallest example in this family, but it was not the first graph discovered. The first graph that was found by Greaves and Cole was a Neumaier graph on 24 vertices. And let me construct it for you. You can see here the icosahedral graph, and it's also its second appearance today because we already saw it in the talk by Istvan Kovac. But here you see the icosahedron graph, and I have colored these 12 vertices in 6 color classes in such a way that these are regular subsets. I mean, if you take any vertex which is not yellow, then it has precisely 1 yellow neighbor. If you have any vertex, it has precisely 1 green neighbor. It has precisely 1 orange neighbor, except if it's yellow or orange itself. And these color classes themselves are co-cliques. Now, what do? We take a copy of this graph, and now we're going to connect all vertices with the same color. So I already started with the black ones. So I connect the black vertices inside the same graph and connect them with the black vertices of the other graph, well, the other copy. And I do this now for all color classes. And this procedure gives me a strictly Neumaier graph on 24 vertices. So this is something that Greaves and Cole discovered 2018. And you could do this actually a bit more general than what they described. So the idea was inspired by their construction. It was more generally described by Akademgorodok, well, last year. And the idea is that you start from a number of graphs which are edge regular and which are, well, have the same parameters as edge regular graphs. So here I took 2 copies of the same graph, but they don't have to be copies actually. They don't have to be isomorphic as long as they have the same parameters. And they must admit a spread of 1 regular co-cliques. So that's what we saw. We had, well, I used colors to indicate them. We have partitioned the graph into co-cliques, and each of these co-cliques is 1 regular. And then you make a new graph with as vertex sets the union of all these vertices, and you connect 2 vertices if they are adjacent in their copy already, or if they have the same color. And the result will be a Neumaier graph if the number of copies, which was T, or the number of graphs, equals lambda plus 2 times k plus 1 divided by v. So in particular, this number has to be an integer. So you find that it is a Neumaier graph with these parameters, and it admits the resulting Neumaier graph a spread of 1 regular cliques. So it doesn't admit a single regular clique, which we require, but it's actually a spread of cliques that it has. Now, we also want to know whether this is actually a strictly Neumaier graph. And if T is at least 2, then you're guaranteed to have a strictly Neumaier graphs. Now, we will see that there are many cases where T is 1, where you also find a strictly Neumaier graph, but when T is at least 2, it's guaranteed. Well, we've proven this, but this was independently also described by Evans, Goryanov, Konstantinova, and Mennik. And apologies if I don't pronounce all the names correctly. So you have this machine, which was inspired by Greaves and Cole, which produces Neumaier graphs if you feed the right thing into it, namely a family of edge regular graphs which admit spreads of 1 regular co-cliques. So you might say at this point, well, you shifted the problem, and that's true. So now we're looking for these kind of graphs, these graphs which are indeed edge regular and admit a spread of 1 regular co-cliques. And Greaves and Cole themselves in their first article said, well, you could take distance regular atypical graphs of diameter 3. And there are examples of such graphs, namely the Taylor graphs, including the icosahedron graph that we just saw. But we also have the Tas-Somma graphs, which exist for the right prime powers, the right powers of prime powers. So it starts with a finite field. And you can do this. Of course, I mean, there is not really an abundance of such graphs because, of course, quite a heavy condition. Distance regular atypical diameter 3. So Greaves and Cole in a second paper gave other graphs that you could use to apply this construction. Now they describe them in a sense directly, So not using this construction, but you can see that it's actually through this construction that it works. And they took Cayley graphs on this very specific group, namely 2 or 3 copies of the group on 2 elements times the additive group of a finite field. Now, this prime power Q needs to fulfill a condition given whether you have 2 or 3 copies of the finite simple group of order 2. And you might think, well, the additive group of a finite field, that's of course a bit strange, because you could just describe this as a elementary abelian group. But in the construction, you will see that they also use, you'll use both the multiplication and the addition on the group. Now, of course, there is a conditional Q, but it doesn't work for any Q that fulfills this condition. So for instance, if you have m equal 2, you see it works for 7, 13, and 19, but not for 25 or 31, again for 37, and so on. And this is, of course, due to the fact that this number t must be an integer, as I said here. So that's what was known. And you can see, if you look at the table, there are some parameter sets. I showed you the graph on 24 vertices. I showed you the graph on 16 vertices. So there are some parameter sets for which the graph is known to exist. Still leaves open a bunch of others. So there is a lot of parameter sets to be settled still. Okay, where do we come in this existence picture? Well, a strictly Neumaier graph on 65 vertices was known, and it was known to several researchers. I mean, you can find it by computer search, but you can immediately see it does not belong to any of the previous families, because all of the Greaves-Coulomb families, well, the second construction needs an even number of vertices, and the Evans-Gordianov-Panasenko construction has e a power of 2, but this thing has e equal to 1. And it definitely doesn't come from any of these distance regular antipodal graphs. So yeah, we're wondering, is this a sporadic example, or is there an infinite family behind it? And let me deconstruct for you this graph on 65 vertices in a way that it will show you how you can extend this. So 65, as you know, happens to be 5 times 13. So 13 is prime. 5 is also prime, but it's an odd integer, and we will see that it is sufficient for 5 to be odd, and that it doesn't have to be prime. And then we take the number 2. And what we do is we take the powers of 2 mod 65. In particular, -1 is among these powers. And this is important, because what you then can do is take the Cayley graph with as vertices the integers mod 65 and use this set of powers of 2 as generating sets. And the fact that -1 is there guarantees that, well, the graph you find will be a simple graph. It's not directed. And this is guaranteed to be an H-regular graph with these parameters. And it has a spread of 1 regular co-cliques. And which are the 1 regular co-cliques? It are the co-sets of the subgroup generated by 13. But this is precisely what we need to apply the Evans-Gordianov construction, if indeed this number t is an integer. And it is indeed an integer because it happens to be 1. So you can do the construction, which in this case means take 1 copy, join the vertices with the same color, so which means just make cliques from these co-cliques, and you find a Neumaier graph. And you can see that it is a strictly Neumaier graph. I mean, it's not guaranteed because the theorem I showed you said t had to be at least 2, but also in many cases where t is 1, as in this case, you find a strictly Neumaier graph. So I hope by this example, I can convince you that you can generalize this. So what you will do is take the powers of some number a, mod n, and then take this set of powers, which has to include -1. And you will take the Cayley graph on this set of powers. And then you need to think about the integer n, modulo which you're working. And indeed, if you take it, the product of a prime and an odd number, and then a in such a way that it, well, has power -1, and it generates the complete set of integers mod p. So it has order p-1 in this group of integers mod p. Then you can do the construction as I just demonstrated for 65. And you find the Cayley graph, which is an edge regular graph, with these parameters. So we know p and q because that's given, and the lambda of the edge regularity is given by this intersection size, and that's important for the remainder of the talk. So this intersection size of this set of powers with the set of powers shifted by 1, because this gives you the parameter of the edge regularity. Of course, this graph has a spread of 1 regular co-cliques. So if we want this construction to work, we need, well, we need to have that this number lambda plus 2 times k plus 1 divided by v is an integer. By which I mean, you of course get this edge regular graph, but if you want to apply the Akademgorodok construction on this, then you need to be able to take an integer number of copies. So this number needs to be an integer, which in particularly means that this intersection size needs to be -2 mod q. So far so good, but you could wonder, well, theoretically it all works nice and you have this one example of 65 vertices, but this might be a very heavy condition so that you have no other examples. But that's not true. You can see for q equal 5, 7, 11, 13, we managed to find examples. In particular, I want to ask your attention for a few particular things. For instance, if you take U5 and P149, taking different A's, namely 13 and 2, you find graphs with entirely different parameters, because here you need to take 4 copies because lambda is 18. Here you need to take 7 copies because lambda is 33. So Q and P are definitely not enough to determine the number of vertices in the resulting graph, because this number A has clearly an influence on it. Second thing I want to point out, you can see here for 13 and 397, both 6 and 20 give a set of powers that result in a edge regular graph which has the right parameters to apply machinery we have. Both have lambda 24, but they are non-isomorphic. So you could take 2 copies of this graph and find a Neumaier graph, a strictly Neumaier graph. You could take 2 copies of this graph and find a strictly Neumaier graph, but you could also combine these two. they are non-isomorphic but have the same parameters. And as I said like 10 minutes ago, this is also sufficient to apply the Evans-Gordianov construction. So there are quite some new examples. This 65 graph that we started with is definitely not alone. It is the first of a big family. Now, some of you might be thinking, well, he said that Q must be an odd number. It doesn't have to be a prime, but all the examples here, Q is very much a prime. That's true. Luckily, also for Q25, which is clearly not a prime, we have some examples. P must be rather big, but that's because Q is already a bit larger. But you can see that for Q25, we can also find a bunch of examples of strictly Neumaier graphs. So this raises the obvious question, is this construction any good? I mean, okay, we can find some examples for different Qs, but how far can we go with this? And for this, we will use some number theory. So the question that I want to address in this section is the following. For which Qs can we find a corresponding prime and an integer a such that the construction that I just showed indeed produces a strictly Neumaier graph? And the first thing that I was interested in myself, and I hope that it's also something that you think is not trivial, is whether there are indeed an infinite number of examples. So can we find an infinite number of examples through this construction? Can we do this already for a fixed Q, or do we need to take several Qs? I mean, do we need to go to an infinite number of Qs, each having some examples? Or can we find a single Q for which there are already an infinite number of examples? Or even better, are there an infinite number of Qs for which we have an infinite number of examples? So we will be looking at this number, the intersection of this power set with this power set shifted by 1, and we want to find out whether this can be -2 or not. Now, the first thing that you've noticed is that notoriously absent in my table was 3 squared, or any multiple of 3. There was no 3, no 9, no 15. And this is immediately clear if you see the following result, namely the intersection size of this power set and this power set shifted by 1 can never be 1 mod 3, just because there is some symmetry in this set. But 1 happens to be -2 mod 3. So if 3 is a divisor of Q, the construction produces no new examples of strictly Neumaier graphs. So Q must be definitely something else. Okay. That was already a disappointment, but we knew there were examples, so we were still hoping for the other Qs. And we could prove the following explicit formula for the size of the intersection of the power set and the power set shifted by 1. Now, if you look at it for the first time, you might think this is an example of a very ugly formula. And moreover, almost all of the symbols that are here, you don't know yet. And that's true. Only this P here is the prime. Well, we know the prime. But all these other things are a bit strange at the moment. So let me introduce them to you one by one. What is it that we are going to do? So we have this integer a of which we are taking the powers. And let's look at its reduction, mod p and mod q. Because we know this integer lives in the integers mod p times q, because that's where we're looking at its powers. So we can look at its reduction mod p and mod q. And n will be the order of this reduction mod q, which we call beta, in the integers mod q. So that explains already the n, which you can see at one place in the two places in the formula. Okay, next thing that we will do is introduce a map from the finite field of order p to the subgroup of the integers mod q generated by beta. Just in a very easy way, alpha to j is mapped to beta to the j. Remember that we required that this alpha generates this finite field, which is actually just the integers mod p. We take a second map now from this group generated by beta to the complex roots of unity, the nth complex roots of unity. And chi is then just the composition of these two maps. And then we have a set B, which is the set of elements in this subgroup generated by beta, so mod q, such that b minus 1 is also in this group. Okay, we see this b is important here. The chi that we just introduced is also appearing in the formula. The psi that we have here is used to define the elements Cij. The only thing remaining is the j, and the j is the Jacobi sum of these two maps, which are actually characters. So Jacobi sum of two characters is given in this way, and we use it here in this formula. So this formula describes explicitly how many elements there are in the intersection that we are looking for. You might say, well, you've shifted the problem a bit to this B, where you still need to check for which elements of this subgroup B minus 1 is also in the subgroup. And that's true. But of course, this B is way smaller because it's only the integers mod q than the full set. And if you choose your beta carefully, then it's actually very easy. So if this is still a bit overwhelming, don't worry, I will look at an example with you. So let's take for a moment q equal to 5. Now, if q equals 5, beta cannot be 1, because then never minus 1 will be a power of a. So let's take it for a moment equal to minus 1. But then you see immediately that the powers that the subgroup generated by beta exists only of 1 and minus 1. So B is the empty set. So you are guaranteed that this thing is 0, because B is 0 and this sum is empty. So all these Cij's are also 0. So the whole thing is 0 immediately. So that's a strong result already. So if you take beta equal to 2, then this psi that I defined as a map towards the onto the complex roots of unity maps beta onto the complex unit I. And you see that you must have that P equals 5 mod 8. And in this case, you apply immediately the formula, and you see that this intersection size equals 1/16 of this sum. So the only thing that remains is to compute these two Jacobi sums. Now, I didn't have to do this because there are books on Jacobi sums by people in number theory. And For instance, there are expressions for this Jacobi sums. And you can express it in the following way. P is 5 mod 8, so in particular it's 1 mod 4. And you might remember from your own number theory class that in this case you can write the prime P as a sum of two squares. Of course, you could still switch the sign of x and y. We will require that x is 1 mod 4, because if it were 3 mod 4, then you can change the sign. And essentially, you do here the same for y. You fix the sign. And then these Jacobi sums, j chi chi and j chi chi squared, can be expressed in terms of x and y. And you find that this intersection size that we are looking for just can be described as 3/16 of p plus 1 plus 2x plus 4y. Oh, that's neat. And then it is the time to use a sledgehammer from number theory. You might have heard or learned at some point in your life that in any arithmetic progression, infinite arithmetic progression, that you choose in a non-stupid way, by which I mean that the first term and the fixed difference have a GCD of 1, but they're co-prime. If you do this, then in such an arithmetic progression, there will be an infinite number of primes. And this is a theorem due to Dirichlet. But the nice thing is that this is not only true for the integers, but it is also true for some other rings, such as the Gaussian integers or the Eisenstein integers. By which I mean the integers, well, the rings Zi and the rings zeta 6, which is zeta 6 the first root of the sixth root of unity, which is not a third root of unity. And also there, if you take an arithmetic progression, so A and M co-prime, then you have an infinite number of prime elements in this arithmetic progression. And of course, by this I mean prime elements in this new rings, not of course primes of the integers. So why did I say this? Because we have our intersection size still for q equals 5. I just replaced here p by its expression as x squared plus y squared. And this thing has to be minus 2 mod 5, so it has to be 3 mod 5. I can rewrite this, and I see a quadratic expression mod 5. Now, quadratic expressions mod 5, that's something I can think about. I can handle this, and I can find these solutions. For instance, x0 and y equal to 1 is a solution for this mod 5. Now, I also want, remember, that p is 5 mod 8. So using Chinese remainder theorem, I will work mod 20 and not mod 5 to ensure that p is indeed 5 mod 8. So I will choose x equal to 5 mod 20 and y equal to 6 mod 20. So that's this 0, 1 solution that I just told you, mod 5. And I know now that mod 20, there will be an infinite number of prime elements in the Gaussian integers, which are indeed equal to 5 plus 6i mod 20. And then the prime, which I find by, well, the integer that I find by multiplying p by its complex conjugate, gives you a prime, an integer prime, which satisfies the conditions. Of course, it satisfies the conditions because, well, here we choose something that is a solution to this equation, and it is 5 mod 8, and it is guaranteed to be a prime, so it works. And there is an infinite number of them. And this actually shows you that for q equals 5, there is an infinite number of primes for which we can then find the corresponding A, such that we have, well, we can construct a strictly Neumaier graph. Now, using some results on Jacobi sums, which I will not go into detail here, you can do the same thing, not only for 5, but also for 7. And actually, for each odd number, which is the product of primes which are 1 mod 6. And for each of these q's, you will find an infinite number of primes and integers satisfying the conditions. So an infinite number of strictly Neumaier graphs. So this construction that we started with to generalize the 65 is actually giving us a very big infinite family. This final theorem is maybe just for the number theory lovers among you. We can even show what the density of the primes is that work. And for q equals 5, this density is 7 over 64. For q equals 7, the density equals 1 over 12. For this general q, we were not able to compute the density, but well, we can do it for the smallest q's. The final thing I want to tell you about is this result, because well, we proved this formula, and it's actually a quite strong thing, because not only it allows us to prove that the construction produces an infinite number of examples, but it also allows us to disprove the existence in other cases. For instance, if you take a q which is divisible by both a Fermat prime, and if you have forgotten what a Fermat prime is, it's a prime of this form, and it's also divisible by a prime which is 3 mod 4, then you are guaranteed to find an empty set as this intersection. So in this case, well, an empty set has size 0, and this is never -2 mod q for q and odd integer. So this means that there are indeed no examples for instance, 35, because that's divisible by both 5 and 7. For 119, because it's divisible by both 17 and 7. So, well, I've discarded here the ones that are already divisible by 3. But we can see here that there are some other q's for which the construction won't give anything. So I have, I think, still 10 more minutes left. So at the end of this talk, which was mainly about constructions and about existence and non-existence, I want to tell you a few things about eigenvalues of these Neumaier graphs, of course. So we know strongly regular graphs have 3 eigenvalues. One of them is the parameter of regularity k, and this has multiplicity 1. We know this. And remember that we started with these Neumaier graphs as things which are, well, close to strongly regular graphs. Because at first, well, Neumaier asked whether all Neumaier graphs are strongly regular graphs, right? And in a sense, their definition is close to being strongly regular. So you could ask yourself, if you have a Neumaier graph or a strictly Neumaier graph, what do we know about its number of eigenvalues? And a first result, which was proved by Abiat, Bruin, Dazeler, and Kohl, shows you, surprisingly, that a strictly Neumaier graph cannot have 4 eigenvalues. Despite being close to being strongly regular, you cannot have examples with 4 eigenvalues. Simons, who is who used to be a bachelor student of mine, showed that there are actually many strictly Neumaier graphs with 6 eigenvalues. Which leaves the obvious open question, what about 5 eigenvalues? So far, no examples are known with 5 eigenvalues. The main thing that we could prove about them is that if they would exist, then the number of closed walks of length 4 in such graphs must be at least this number. Now, if you have a graph which is randomly edge regular, then this is roughly the number of closed walks of length 4 you would get. So it must be clearly more than this. Let me also tell you something about the small eigenvalues. So we know if we have a strongly regular graph, it has 3 eigenvalues, k, then one which is larger than 0 and one which is smaller than 0. And Seidel already classified all strongly regular graphs where the smallest eigenvalue is at least -2. So you could ask the same question about strictly Neumaier graphs with smallest eigenvalue at least -2. But if you combine the results of Dub-Svetkovic and Abjad, Vrandazreer and Kool, then you can see that a strictly Neumaier graph must have smallest eigenvalue smaller than -2. Which raises the obvious question, yeah, well, how large can the smallest eigenvalue of a Neumaier graph be? And we could find this nice connection between the smallest eigenvalue and the parameter E of the strictly Neumaier graph. Now remember, so far we only know one family where E is not 1, but we can see that E in generally is bounded by the smallest eigenvalue, by a polynomial of degree 5 in the smallest eigenvalue. Well, this brings me to a few open questions on this topic, and I've addressed most of them already during the talk. First and foremost, of course, are there strictly Neumaier graphs which where E is not a power of 2? I mean, for E powers of 2 and E equal 1, which is also power of 2, we have in the meantime several constructions, but E different from a power of 2, we don't know anything. Related to this, the question, can we find Neumaier graphs with a large E and a large smallest eigenvalue, maybe close to our bounds? The bound is now a polynomial of degree 5. I guess it should be able to improve this, but well, we couldn't manage so far. But for instance, for the family that is known with large E, it's definitely not degree 5. So maybe there's something else possible there. And then, of course, the question, are there strictly Neumaier graphs with 5 eigenvalues, which is still very much open. And then on the construction side, well, the construction that I just described uses the ring of integers mod p times q. Can this be generalized to other rings? This would be very interesting to see. So this is some work for the future. Well, I guess that was also. Thank you for your attention. I'm happy to take your questions.
Maarten, thank you very much for a very nice talk. Are there any questions to the speaker?
Maarten, that was a beautiful talk. Do you have a reference for that result of Neumaier generalizing Dirichlet's theorem?
Yeah, well, then I will for a moment search for something else, namely You can still see my screen, I guess.
Yes. Yeah.
Where is, well, let me do this in a smart way. So the book on class field theory from Neumaier from '86 is what we used.
Okay. Okay, thanks. Because I think I can use that generalization in a different context, but I wasn't aware of it. I knew Dirichlet's theorem, but not the generalization. That's great. Thank you.
You're welcome.
Okay, any other questions, Maarten? Okay, I just wonder, can you say something about integrality of these graphs? I mean, are there integral graphs, Neumaier graphs with 6 eigenvalues? I mean, containing only integral eigenvalues.
Yes, there are, and I'm going to switch again to something else. Of course, this is this is what I'm looking for. So I mentioned to you I had a bachelor student who well, was very good with computers, so I made him implement a bunch of examples. So for instance, if you take the Johnson graph G63, which is a Taylor graph, so you can do the original Greaves column construction, you find a graph on 6 eigenvalues which are all integral. And there are some other examples in this table, but not so many, but this one also is an integral example, and the bottom 2 rows based on the Gosset graph are also integral. So if this answers your question.
Thank you very much. Yeah, interesting. Okay, any other questions to Maarten? Well, if not, then let us thank him again for this great talk. It was really interesting to get the new information and some new questions. Thank you very much. Yeah.